How does leader election work in Apache Kafka? Well, hang on, back up a second. What even is leader election? Why do we need it? How does it work? What's it doing for us? Well, it's actually at the heart of how Kafka stays highly available. And in this episode of Streaming Audio, we're going to go for a deep dive into the mechanics of it, why we need it, how it works, what can go wrong, and how it's currently being improved for even higher uptimes. Guiding us through is Adithya Chandra, who's a staff software engineer here at Confluent, and he works on Kafka's scalability and performance. And this turns out to be his story of an elegant design with some interesting trade-offs along the way, and just a little bit of a kind of Pokemon hunt as we go looking for those 1 in 10,000 cases that get in the way of 4.9's availability. This podcast is brought to you, as ever, by Confluent Developer. More about that at the end, but for now, I'm your host, Chris Jenkins. This is Streaming Audio. Let's get into it. So I'm joined today by Adithya Chandra. Adithya, how are you doing?
I'm doing great. Yeah, thanks for inviting me to the podcast.
Thanks for joining us. We're going to get really technical on this one. We're going to have a deep dive into leadership election, right?
Yeah.
Because you work on, let me get this right, you're a staff software engineer here at Confluent, and you work on scalability and performance, and particularly at the moment on leadership election stuff.
That's right. So I've been at Confluent for like 2.5 years, and I've primarily focused on the Kafka performance and team. And as part of performance, we've looked at running Kafka cost effectively, which is primarily getting the right price performance ratio in terms of hardware and our cloud configurations.
Okay.
And then I've also focused on scalability, which is like, we now support like more than 10 gigabytes per second on our Kafka clusters, which is basically running larger clusters with a lot of instances, and also, running larger instances with a lot more memory and a lot more CPU. And finally, we've been focusing and looking at very closely to make sure our tail latencies in Confluent Cloud, uh, we bring them down in a systematic manner. So we've been able to build dashboards and probes to measure our latencies accurately. And then we've been constantly iterating on finding the bottlenecks and fixing them over time. And that is one of the places where we've had to enhance leader election that's currently there in Apache Kafka. And that was my how I started working with leader election and looking at it.
Okay, cool. I have to ask, is that how you prioritize work? You just see where the pain points are and
Yeah.
just look at the
Yeah,
latest burn?
yes, exactly. For the performance team, it's all about finding the bottlenecks. It's like kind of like peeling the onion, right? Like if we find one thing and fix it, we may think, oh wow, it'll come down by a lot, but you just hit the next bottleneck. It comes down by a bit, but you find the next bottleneck. And the super unique thing about the cloud is we look at all these customers running all these different kind of workloads. So the bottlenecks are very different and they change from workload to workload. For example, it might be compression and the type of compression scheme that you're using. It then just relates to, like, say you're also using compaction or you're using an older version of the Kafka protocol, and we're doing up conversion or down conversion on the broker. So there are all these slightly different workloads which are interacting in weird ways and taking latencies up and down. uh, the average cluster and the average on average the latency that we see for Kafka is incredible, right? Like 10-20 milliseconds is kind of what we see.
Yeah.
But at the edge is where what the interesting thing is, like the worst clusters, you might say, the worst latencies. So that's kind of what we're looking at, and that's where all these edge cases come in.
Yeah.
And then we've been slowly improving them one by one.
Those random surprising edge cases are where you find
Right.
all your fun.
Right.
Cool.
It's super interesting. We find them one by one. The fixes are small, but it takes a lot of monitoring, a lot of understanding of the entire system, the whole stack, the life cycle of a request.
Yeah.
And then you find the small thing that, hey, why are we doing it like this? Why not do it like that? And you tweak a little bit, and you can get pretty big wins, which is surprising. But we're also working on, like, taking a longer term view, and, like, thinking about the architecture. That's also happening in the side.
Yeah, yeah. It's one of the things I love about performance tuning is I wish the same rules applied to other parts of my life. I wish I could really study the cost of a car for a few weeks and then finally get the price down to a tenth of what it was before. That would be nice, wouldn't it? But those kind of numbers only work in performance tuning. They don't work in everyday life.
Yeah, I think there was a saying somewhere that, like, if you can bring down your performance by like 20%, then you've done some great engineering work. If you've brought it down by 2 or 3x, then someone else had done a lousy job. So
Yeah. Yeah. Okay, so without pointing fingers of blame in any direction, we best talk about leadership election. But let's take this from the start, because not everyone will have the depth of knowledge that you do. Right. So let's see. I have this logical model in my head that Kafka is a bunch of topics, essentially log files, split into partitions, usually partitioned by key, and each partition is replicated 3 or more times, right?
yeah.
For resilience. So with that basic model in my head, where do leaders come in first?
Yes, so that's a fantastic question, right? So you have three replicas, which are exact copies of data, and the client is writing to these three replicas. You have a bunch of different ways that you can do it. The
Yep.
way Kafka does it is that it elects one of those three replicas as the leader. The advantage of this architecture is that the client, either a producer or consumer, only has to write once to that particular replica. This allows us to reduce the amount of traffic that we write over the internet, assuming the producers or consumers are in a separate place compared to where you're running your Kafka broker. And the other advantage is that it's a reasonably simple system, right? Like, the client doesn't have to worry about failovers. It doesn't have to worry about whether the replica is caught up, and what if there are holes in the log, and all those things. All it needs to, and all that is handled behind the scenes on the server side in Kafka. The
Yeah.
clients just have to figure out who's the latest leader, which they do by refreshing their metadata. Uh, and that's where leader election comes in. So the leader election is basically, you have three replicas, so you have a choice of which one of the three should be leader, and we have
Yep.
a bunch of different factors that we consider when electing them leader. And
So
then
in our just to check, so in our case of three replicas, we've got three brokers that are all writing to their topics, but one of them's receiving from the client and the others are receiving from the leader.
that's right.
Right.
So let me talk. I'll just go through the entire the life cycle in a little more detail. So what's happening is the client is writing records to the leader, the producers, and even consumers are consuming records directly from the leader. This also has a good performance benefit, that your data, typically most Kafka use cases are reading data that was just written. They're not reading historical data, right? Like, there's new real-time traffic coming in, and you're consuming it pretty quickly. So this
Yeah.
is typically hot data, and it's in the cache because you've just written it. So if someone else reads from the leader, we already have it in memory, and we send it to them. So that's another advantage of this leader model. And the followers, what they're doing is they're using the same protocol, the same RPC, a similar RPC message as the consumers to fetch data from the leader. So the leader gets
Right.
a message, it writes it to its local log, and then it waits for these followers to send the fetch request, and they catch up to this data. But by default, what we do is we don't respond back to the client. So let's say you got a batch of records, the
Hmm.
leader wrote it locally, and then it waits for the followers to get the same data, write it locally, and then send an acknowledgement back that they have written data locally, and only then it responds back to the client saying, hey, all the data has been committed and persisted. What this
Okay.
allows us to do is as long as a client has got an acknowledgement, then we are sure that all replicas have that data. And any of them at any point can be safely elected leader without any data loss. I'll take a pause if you have any questions.
Right. So, yeah. So the one question I have there is, so each replica is responsible for pulling. They're not
Yes,
pushed to the replica. The
yes,
replica pulls.
yes.
Okay. Why?
This is something that we've been discussing, push versus pull. There are advantages of push. Pull makes a lot of things simpler, right? Like it's like data is on the leader. We're using the same mechanism that followers are using. It's simpler to implement. And you can get a lot of the biggest advantage, I would say, of push is that you can send it immediately. And you don't have any, for example, delay when you're pushing data, which is
Yeah.
fantastic. But push is also slightly more complicated. What if the follower can't take the data that you want to send? Then you'll have to wait, you have to retry, and you have to, and also performance throughput versus latency is a dance that we constantly play in
I can
performance.
imagine.
You
Yeah.
don't want to send, like, let's say you're getting small records. If you send them all as soon as you get, you may not get the best throughput, and you may burn a lot of CPU in the process. So we want to batch it together and then decide what would be the ideal batch size that we want to send to the follower. So in the pull model, it's easier that the follower controls this. It knows the rate at which it wants to pull, and then it'll pull that data. Uh, One thing that I didn't talk about was what if somebody is slow, or what if somebody is down. If we keep waiting for this particular follower which is down, then our latencies would be terrible, and we would never respond to the customer. To deal with this, what Kafka does is it keeps a list of replicas, what it calls in sync replicas, or the ISR.
Right.
And the ISR tracks all the replicas that have successfully, have been copying data from the leader. And this is persisted in the metadata.
Okay.
And these are the replicas that are eligible for leader election. If a replica is not in the ISR, we don't consider it for leader election, unless like there is an unclean election flag where you say, hey, I want to trade off durability or correctness guarantees for availability, which we don't recommend. But if you do that, that's the time where
Right.
anyone
And
can be elected.
when you say it's tracking, I'm just trying to get all the details here. When you say it's tracking which clients are in sync, is that they're acknowledging that they've got up to offset number X,
Yes.
and only the people who are in the same offset as you, the leader, are considered in sync?
Yes. So basically, the leader, what it's tracking is, hey, these are my followers, and they're constantly sending me these fetch requests. And the fetch requests that you have served, you served all the data that you had. So they're not like, lagging a lot. They're not, we also keep track of the lag, how far behind they are, like you said, in terms of offsets. But typically, because it's a batch call, when the follower comes back and says, hey, give me all the data that haven't yet received from the last time, it'll
Mm-hmm.
send like a fetch offset, which tracks, like, what was the last point till which it successfully replicated. So we know all the new data from that fetch offset is what we should send back to the follower. And that's kind of what we send back. So as long as we are sending it back, we assume that it's in the ISR. There's a setting which can control, like, how far behind the followers can be. It's set to, like, say, you can set it to different numbers, like 30 seconds, 40 seconds, and that's kind of how long you wait. And if a follower is behind that, you will kick it out of the ISR, and you'll shrink the ISR basically.
Right. Right. Okay. I think I've got that in my head, how it works when it's supposed to be working. And yeah, it does seem a lot like the normal producer and consumer considerations you have.
Yes,
Right. The
it's
producer's
pretty.
batching things up and the other guy is consuming.
Yes, exactly. So
Yeah.
that's the great thing about it. And yeah, it's exactly the similar code path as the consumer. There's one interesting thing about fetch sessions, which is an optimization where we kind of if you have a lot of partitions, the follower doesn't have to constantly tell the leader, because it's a pull based model. If you have no state maintained on the leader, then each time the follower will have to tell, hey, these are all the partitions and these are all the fetch offsets that I want to get data from. And it can become, the request can become more expensive than the responses that you're sending for these fetch requests. To speed that up, there's something called fetch sessions, which tracks on the leader side, hey, what are all the partitions that are currently in the session, and if there are partitions for which you're not sending any data, then the follower doesn't necessarily have to send it in its next record. So that's kind of an optimization that we can do.
Oh, right. So you're essentially keeping a list of things the followers subscribe to.
Yes.
Yeah. Okay. That makes sense to me. Okay. Right. Let's move on to the disaster. We've got that model all working just fine. What can go wrong?
Yeah, so a bunch of things can go wrong. The most obvious thing is you're doing an upgrade and you're shutting a broker down. And let's say you have three replicas, one of them is leader. Actually, let's start from even before that. Let's say you created a new topic and you have three replicas assigned to it, and which one of them is elected leader. So when a new topic is created, the controller decides which are the brokers that will be where the replicas will be assigned. So let's say there's a new topic and a partition where the replicas are 1, 2, 3. uh, the order of this replica list is important. The very first replica in that 1, 2, 3, we call it the preferred leader. uh, and I'll come back to preferred leader, but the most important thing is that this is the broker that will be given preference during leader election. And this kind of allows you during placement to decide how leaders will be placed across the board. So let's say we have like these you know interesting models which track like cluster performance over time, and they're we have SBC in Confluent Cloud, which is tracking like what's happening with CPU, with network ingress, etc., on each of the brokers. uh, and then we're taking decisions on like how is where should leaders be. And the best thing that you can do at that point is think about where the preferred leader should be, and that's typically the first uh, the first broker in the replica assignment. And whenever there's a disaster, like someone else will be elected leader other than the preferred leader. But Kafka also gives you a setting called balancing. What you can do is you can run a preferred leader election consistently. So let's take an example. Let's say the example I gave you, 1, 2, 3. One was the preferred leader. Everybody, all the brokers are up. There's no data, and
Right.
one was elected leader. And now we are electing 2 and 3 are in the ISR. Nothing funny is going on. And after some time, you decided to upgrade broker 1. So you took it down.
Okay.
So you issued something that we call a controlled shutdown, at which point broker 1 will tell, hey, I want to give up leadership. So this is another trigger for leader election. And then
Right.
when it says I want to give up leadership, the controller will go and trigger a special leader election where it will ignore this broker 1 in the set of replicas that need to be elected leader, because it knows, hey, this guy is giving up leadership and is going to go down. So
Yeah.
1 of 2 or 3 will be elected leader. And then broker 1 can now yeah, if you had a
Oh,
question.
I'm just. I'm wondering how it chooses between 2 and 3. Who makes that decision and how?
So right now, the controller only cares about conceptually, all we care about is who's in the ISR, and then it does not really matter whether it's 2 or 3. But right now, I think it's just taking the first one in that list, so it will be 2.
Okay.
But that can change. So there's nothing like, it doesn't matter whether it chooses 2 or 3 in this particular example. Uh,
Right. So
and
logically it chooses one at random. In practice, the code probably just picks the first element of the array.
Right.
Yeah.
That's
Okay.
exactly right.
Okay.
And so now, yeah, two became leader. And what happens next is you upgraded it and one came back. So if you don't do anything, two will continue to be leader. But your load may now no longer be balanced because when you initially created it, let's say you gave one leader to each of those. There's some other partition's leader which is on two. And now even for this partition, the leader has moved to two, and two is kind of doing more work than it's supposed to.
Yeah, because you could have deliberately created your partitions with like the first one is your largest, most expensive, fastest machine, and the other
Yes.
two are kind of backups. And
Yes,
now
you
you
could
failed over
also.
to two as your cheaper redundancy machine.
Yes.
Yeah. Okay.
And that's something that, like, I've also seen people do and ask for, like, basically exactly what you said. Like, you have the first one is where, like, you have these expensive and, like, in the main data center as your client applications, and then you have these redundant models which are in a different data center, and they're mainly for disaster recovery. They're
Yeah.
copying data, and you just fail over, and now we want to fail back into your primary data center when it comes back. And
Yeah.
that's where you use this preferred leader election strategy, which
Okay.
is it allows you to set this periodic interval at which we will run preferred leader election. So let's say we set it for 5 minutes. So every 5 minutes there is an event in the controller, and it goes and tries to trigger a preferred leader election for all partitions where the leader is not the preferred leader. And
But the
then,
leader is now available again.
yes, and then if
Yeah.
the
Yeah.
preferred leader is in the ISR and available again, then it will fail back into the preferred leader, and your load will move back to this instance.
Okay. Because I can imagine people, at least if they don't have that, I can see people deliberately shutting down two just so they can push the leader back to one and then bringing two back up, right? I bet
Yes,
that happens.
yes, that would be, yeah, yeah, that's another way to do it. You're right.
But now we have an automated mechanism for it.
Yeah, no, we are, yeah, yeah, you're totally right.
Okay. What about, is that it for graceful failover? Is there anything else we need to know, or should we move on to disastrous failures?
Yeah, so the main thing for a graceful failover that you have to think about is there's another setting called how many of these in-sync replicas should respond before you acknowledge back to the client. Uh,
Right.
so you can say, so the default is ax equal to all, where all the replicas in the in-sync replica list have to acknowledge a particular write before
Yeah.
you respond back to the client. And this model is very clear, right? Like, everybody's replicated the data, and any of them can become leader. There's also cases where people don't really care that much about data loss, and they set ax equal to 1, where it's just written to the local log of the leader, and none of the followers have potentially replicated it. And they'll replicate over time, but you don't wait to acknowledge to the client. So, and
Yeah.
in this world, if there is a failover, we still have in sync replicas, everything, and consumers don't see the data till it's like replicated. But it's just that the producers, like, can move fast. They just write and they just fire and forget about it. So if
Yeah.
there is a failover, but your producers have thought, hey, I've successfully written something, that may disappear during a failover if you had ax equal to 1.
Right. I think what I want is somewhere in the middle, right? Because I don't want to lose any data if I lose my leader ever,
Hmm.
personally, but I don't want a follower to go down and take my cluster down. A single
Yes.
follower.
Yes, you're
So what
totally
do I
right.
do about
That
that?
is exactly what we want. Uh, So one way people do something like that is with quorums, where they will wait for some subset of followers to have replicated data before they move forward. But in Kafka, with the in-sync replica, replication model, we can't do something like that. So that is why we wait for, all the in-sync replicas to replicate, and we depend on the ISR shrinking. So basically, one of the replicas is not able to catch up or is slow. We want to explicitly kick it out of the ISR. And then we no
Right.
longer wait for it during this hot path of new requests coming in and replicating. So let's say you have three brokers. Like you
Yep.
said, one of them is slow. It's not replicated, it's below behind, let's say 40 seconds since it's replicated from your log. Then the leader will explicitly kick it out of the ISR, and it will
Right.
no longer wait for that guy. So you still have performance, but it's not done in a more real time manner. Like at any time, it's not like your writes can go to some subset of the three. It always has to go to all the replicas in the ISR.
Yeah. So
That's kind
instead of saying I want to make sure I've acknowledged 4 out of 5, I do everything, but that number 5 could shrink dynamically to 4.
Yes,
Right.
yes. And
Gotcha.
the biggest advantage of this model is you can potentially run with two, and we would still be correct, and we would replicate to two, and then things are fine, and then one of the two can go down, and you can go down to even one, and that would still work. So that's the advantage of this flexible
Right.
model of shrinking the ISR and growing it back.
Okay, I see that. Okay, so are we going to move on to when, like, someone accidentally pulls the plug out of the leader?
Yes. So yes. So if someone accidentally pulls the plug out of the leader, uh, what happens is we have Zookeeper and Craft where things work slightly differently, but in both
Hmm.
cases, there's a way. So in Zookeeper, the broker keeps connections and heartbeats, and we know if the broker is alive and reachable. So what we
Hmm.
care about is this broker part of the cluster, and as long as it's part of the cluster, the controller will assume that it's the leader and things are working correctly. But let's say something went wrong, we lost the Zookeeper connection, or the heartbeats in Craft aren't working. Then in that world, that broker is no longer eligible to be the leader. And that's the case you are talking about. And the controller maintains this list of alive brokers, where it will take it out of the alive broker list and it will trigger a leader election. This is slightly different from the controlled shutdown, where the broker is giving up leadership, in the sense that it's flushing everything to disk, it's making sure its local logs are written, and then it's giving up gracefully. In this
Hmm.
unclean world, data was not flushed. There was something that you might have written. For example, you've not acknowledged back to the client. You've written a whole bunch of offsets, but we were waiting for the followers to replicate. So this uncommitted data will be lost. So one of the followers, similar to what happened in the graceful shutdown, will be elected leader. So that part is pretty similar. And
Hmm.
then where the point up to which it has replicated is what all the other the new once it becomes leader, the new followers will say, "Hey, this is what the log of my new leader is. I should truncate my log and start from that point." Because it
Right.
has all the acknowledged data is supposed to be replicated everywhere. You will not lose any acknowledged data because you're waiting for x equal to all, and it's guaranteed that the
Right.
follower has got up. So that's
So
kind of
you
how
really
it
do
works.
have to wait in the producer until you've got confirmation that your record has been written.
Yes.
Yeah, as a
Otherwise,
client.
you can potentially lose that. Like, there's no guarantee that it will be
Okay. Yeah.
persisted if there's a failover.
Right. Gotcha. How long does that take? I mean, in both cases, what's the time to get the new leader in a clean and an unclean shutdown scenario ish?
Yes, it depends on a bunch of things. So instead of giving you time, I can talk about all the different things that need to happen in the Zookeeper world and in the Craft world, right? Like in the
Yeah, yeah.
Zookeeper world, what needs to happen when let's say a broker goes down is that first the Zookeeper connection has to break, and then the controller gets to know, hey, this broker is not alive, however long that takes.
Hmm.
And then the controller decides, hey, this needs to it triggers a leader election, which is typically very fast, let's say microseconds, and then it decides who the new leaders should be. So there's also a caveat here. It depends on the number of partitions that were hosted on a particular broker. So for our examples, we've been considering one partition, but people typically run thousands of partitions. So it has to literally do leader election for all 1,000 of them. So that's another factor that goes into how long things
Oh,
will
okay.
potentially take. And then what happens is it needs to send metadata changes to all the other brokers, saying, hey, you know what? These are the new leaders, because some of them would be elected leaders for different set of partitions depending on how they were distributed across the board. So it potentially has to send all the other brokers in the cluster. So if it's a large cluster, it might have to send these requests to a large number of brokers. And each of them would then process it and decide, hey, I am the new leader. uh, you use something called epochs, etc. But basically, what it boils down to is each of these will make a state change and say, "Hey, I am the new leader,
Mhm.
and this is what is happening." Like, it'll say, "Okay, I'll start taking rights," and at that point, the followers also have to realize that the old leader has failed. So they'll get a metadata change, message,
Mhm.
and they will go and start replicating from the new leader. And the clients themselves, they might be writing to the old leader. If the old leader is down, they'll have a connection failure. They'll have to refresh their metadata. So that's another call that goes in. They refresh their metadata and they see, oh, you know what? This is no longer the leader. I have to connect to this other broker, which is the leader. If you already have a connection, then that's
Yeah.
great. You don't have to create a new connection. But over that connection, you will go and start making requests to the new leader. And as long as the followers also have a connection between that new leader and everything is set up, your data, they will probably immediately send fetch requests and fetch that data and replicate internally and then act back, the normal replication process. And that's when it'll start moving on. So that's how long all the steps that need to happen in failover. But it's pretty fast typically.
It sounds like a lot of steps, but how are we talking? Seconds,
Yes,
milliseconds?
typically seconds and faster than that. That's
Yeah.
kind of how long it takes. It depends on how fast each of these RPC calls are. If they're typically in tens of milliseconds, then it's pretty fast. It's just a bunch of communication that has to happen, and each of them is fast. Then you will see failover. It's pretty fast. And like I said, it depends on the load. If you have thousands of partitions, that's kind of when it starts taking longer and longer for all
Yeah.
these messages to go out from the controller. And
I suppose if you're not replicating events anymore, you've freed up a bit of network bandwidth for this chatter.
yes.
Right. So I hadn't quite realized this, but there's potentially a different leader for every partition.
Right, right.
Is there some mechanism to kind of spread the leaders evenly around all the different brokers?
That so by default, Kafka just round robins assignment. So when you
Okay.
create a topic, it starts saying, "Hey, I'll put the first leader on the first broker, the second leader on the second one," and then it goes along. And it also tries to, I think, be smart about what was the last time I started putting in my round robin, so that you don't always start from the, let's say you have 10 brokers and you just have a replication factor of 2, you put in 1 and 2. You don't want to start again from 1 and 2 and keep putting things in 1 and 2. So it
Yeah.
keeps track and then it tries to round robin. But that's pretty much what it does. The tricky
Okay.
part is, like, you can, I think this changed a bit in craft. I haven't looked at it recently. I'm not sure if it's still round robins or picks at random, but that's kind of the strategy, to spread it uniformly, like you said, across all the brokers when you create a topic. That's but the problem is, you don't really, this is not sufficient, because you don't really know what is the workload of the partition and the leader. Because
Yeah.
for workloads where, like, you have a single use case, and then you create this one partition that is used evenly across all brokers, and you have the exact number of partitions as the number of brokers, life is good, because producers are probably producing uniformly. But there are use cases where, people use, there are different teams in a company which are reusing the same Kafka cluster. They have a bunch of topics, they all have different kinds of workloads.
Mm.
Then it becomes important to dynamically change this. And that's when we want to model the workload, and then dynamically change which leaders are on which brokers. And that's where, self-balancing, etc., which is not there by default in Apache Kafka. And you have to use either SPC, or there are open source tools like Cruise Control, which do some of these things for you.
Okay. So I guess that leads into a bit more about the work that you've been doing to optimize leadership elections for Confluent Cloud, right?
Right.
Tell us
So
some about some of that.
yeah, so this is what I'm pretty excited about the work that we've done over the past year or two. So it's primarily around, like I spoke about all the things of when leader election was triggered, and then it was always when the broker died completely. But in practice, this is not the only way or the only failure mode, right? Like what we talked about is the broker's cluster membership failed, which boiled down to its connection with Zookeeper failed, or its connection with the controllers in the craft world failed. But we have all these interesting cases, like we discussed earlier, where you would run your leaders in this day important data center, and then you might have followers in another data center for failover.
Mm-hmm.
Even in the cloud, we distribute our replicas across three different availability zones, which are potentially three different data centers. And the reason we do it is, even if an entire data center blows up, you'll have other data centers that we can fail over to.
Yeah.
But the problem here is there are different connections. So you'll have, let's say, external connection to one data center can potentially be broken, but the data centers can talk to each other internally. So this is kind of what we say a particular network, line was broken, like a cable was cut. And in
Yeah.
this weird scenario, we would have leaders that your clients can't connect to, but can talk to the controller, and the controller thinks it's the leader's healthy. So you have
Yeah.
this weird case, which we had to solve to improve our availability. And
So that was
then
actually happening in the field.
yeah, it happens very frequently. And the more obvious one is we have load balancers in front of these brokers. And again, the load balancers for availability purposes are per data center, right? And
Right.
let's say one of the load balancers had issues and went down. They're also replicated, etc. But you can imagine cases where something went wrong with that service,
Yeah.
similar to how things go wrong with Kafka. Then again, you're not externally reachable. And external reachability is super important, right? Like your leader, you can't receive
Yeah.
requests or respond to events, then you're pretty much unavailable.
Yeah.
So
If
that
you
was
can't
a
talk to it, then it doesn't really matter that the cluster thinks it's happy, right?
Exactly. So that was a
Okay.
very frequent thing, and we were thinking about how do we solve this. The first part was detections. There was a lot of work done around network probes, and we have these other things that are constantly trying to send traffic through the load balancer and trying to figure out, hey, is the broker reachable? We also have added new things where the broker itself tries to see, like, is it externally reachable? Is it getting a request from our health check probes, etc.? Is it
Yeah.
receiving node traffic, etc.? And this information is what we wanted to feed into leader election. But at the same time, we wanted to keep it pretty extensible. This is one use case that I gave, but
Mm-hmm.
there are other cases like performance problems, right? That's what my team is mostly focused on. And performance problems are frequent, and typically we know why it's happened if we have fine-grained alerts. But a lot of times we may not know what's happened, and we've just got a monitor which says, "Hey, the latencies are high for this cluster," and then the
Yeah.
on-call goes in, and the first thing that you typically want to do is to just fail over leadership, because leadership failover is super cheap. Like we already discussed, that all you have to do is send these metadata requests, and then the replicas are already caught up, and then the client just has to, and it's already probably connected to the replicas because some other leader is on them, the other brokers, and it just has to send requests to that guy instead of the current guy that it's sending requests to.
Right. So we
um,
don't know why the leader's slow, but let's just fail over to someone that isn't slow while we figure it out.
Exactly. And that's super cheap compared to, like, say, shutting down the broker, where suddenly you'll have less capacity overall. But also, the main problem of that is now you're no longer replicating three ways. So that guy is not, it won't be caught up when it comes back up. it has to catch up all the data, and also you're susceptible that if one of the other two goes down, then you pretty much have an availability, because we set our minimum ISR size to be 2.
Yeah.
uh, so that's the reason we piggyback on leader election. And the way we've extended this to capture all these cases is we've added something called leadership priority. So basically, what it allows you to do is it allows you to go and say, this is primarily just in Confluent Cloud, this is not in AK. It
Okay.
allows you to go and set, hey, the leadership priority for this particular broker is low. I think something is wrong. And we typically call it a demoted broker. So you can demote that broker and the priority will be low. And when we do a leader election, we do something smart. What we do is first we go and do a leader election without these, low priority brokers.
Right.
And if we are able to elect a leader, then that's great. Like, everything's good. So we have leaders that we can elect without taking these guys into account, and those are the guys that will be elected. But let's say there are cases where somebody is not in the ISR, something else has happened, and we cannot pick the healthy broker as the leader. In
Yeah.
that case, we favor availability for performance, basically. So we will just say, hey, nobody else can be elected leader, it's okay, we'll just elect the demoted guy as the leader. And
This is this is dangerously reminding me of British politics, where you don't elect the best leader, you just elect one you can elect. But let me try and stay off that.
yeah, that's
Okay. So you're electing the best leader available. The how is that? How is that triggered? You can say just in Confluent Cloud, this is a low priority leader as the maintenance team behind the scenes, and
that
then
is
that automatically triggers an election, or what is it?
Yes, that's exactly right. So that's one path to do it. So we've
Mm-hmm.
introduced, like, it's an API, an RPC call. So one path is we have these command line tools and all our operational tools which will make that API call, and an operator can just, like, it's almost like clicking a button, and you can say, hey, this broker has lower priority, and it'll
Mm-hmm.
send this request to the controller, and the controller will trigger an entire leader election for all the partitions that's hosted on that broker, and it moves things off. And then when you promote it back, it'll again trigger it and move leaders back on. So that's kind of what happens. But it's not just through that. We also use it for, like, for example, I spoke about our network probes and our network monitoring. So we have a network health manager which is looking at the network health across the board. And when it sees that, hey, the external connectivity is not working for a particular broker, then it triggers this leader
Okay.
election, and then that broker is given lower priority and it won't be leader. And we're also extending it to storage performance. So we have the storage probes where we're measuring how fast is storage for a particular broker. And if you're slower than everyone else, so that's when our tail latencies go up. Let's say the storage for most brokers is taking like a millisecond or less than that to write. But you have
Mm-hmm.
this one broker, which we see this very frequently again in the cloud. That's why we built these things, right? It's taking like 50 milliseconds, 100 milliseconds, and the overall latencies are in like hundreds of milliseconds. In that world, what we will do is, we move leadership off this guy. We say, hey, this guy is slow. We detect it. And the same mechanism, it calls the RPC call, which will trigger the entire leader election we've talked about, and leadership moves away. And then the interesting part about storage is that these guys are still followers, so they're still writing.
Mm.
Um, and as they're writing, we will still get to see if the disk is bad. And when the disk gets better, you can move leadership back to that particular broker,
If it's the preferred one.
if it's the preferred one.
Yeah. Yeah.
You're right.
That is smart, because the thing that always worries me about these automated failure detection things is what happens if it's a false positive, right?
Right. Right.
But you're not actually taking them out of the cluster. You're just saying that lower their priority,
Right.
so
Right.
they're still available. Yeah,
So that
that's
was, yeah, that's a great point. So that was a very conscious design choice, that we won't take it out of the cluster. We're just choosing the best leader. but you still have an interesting point, and it's something that we've been baking into all parts of our software. It's pretty interesting actually, because like, what do you do if you're expanding a cluster and you have one of these brokers that's kind of degraded? Or what do you do if you are, like, shrinking your cluster and you have one of these degraded guys? Like, do you pause all your maintenance activities? And then, even though we are saying we don't take it completely down, you're moving majority of the workload off of it. So, like, your cluster is no longer at full capacity because we kind of have these brokers which don't have any leaders.
Yeah.
Leadership typically is way more expensive because it's doing both reads and writes, and some customers can potentially have thousands of connections with a leader. uh, that's another thing. And also, you'll have to keep in mind that the followers are also replicating from the leaders. They are also sending requests constantly to it. So a
Yeah.
leader does a lot more work than the followers. So if you have a broker without leaders, then its utilization is actually pretty low compared to, on average, we see it almost like, at least 50% less utilization when it's not taking on leadership.
Right.
um,
And that makes it all the more important to make sure you've got the leader on something that's very healthy.
yes.
Yeah.
Yes.
Okay. How long did this this bunch of changes take you to put in? Out of curiosity.
It's been going on for quite a bit of time. Like, I think we started sometime last year, and it's already been a year and a half. But there's so many pieces that it touches, right? Like, there's just the leader election part, which is just one part of the puzzle. Then
Mm.
you want all this detection, and like you said, you don't want false positives, and you want
Yeah.
it to work. I've not even spoken about. I've just been talking about leader election, but you also want to be smart about the followers, because like we talked about the replication model, and the followers can potentially be slow and hold back your latencies, and you can have slightly higher latencies. So that's also another thing. Like, you can be smarter about the when you shrink the ISR, when you expand the ISR. We've been thinking about it, and we've been making slow progress. And like, now Confluent Cloud has 4 nines of availability, uh, and all of these were super important to get there. Like, no, these networking issues where suddenly the leader is not available was a big deal. And we are seeing all these weird things in the cloud. When you bring up new instances, suddenly the storage might be slow. uh, the network might be flaky. It's network attached. If it's network attached storage, you'll see flaky stuff there. So there are lots of these small cases where, like, we start seeing performance problems and availability problems. So we want to detect them one by one, improve confidence. And it's going to take a lot more time, I guess, for the monitoring. And that's where I think a lot of the algorithms and the intelligence is, the detection and figuring out when is the broker completely healthy versus when it's not healthy.
Yeah.
And the election bit is also interesting, but it's not that, like, as hard as like getting the rest of the things, right.
Yeah. But it's this thing, right, isn't it, where if you want 4 nines of availability, then you have to face the cases that only happen 100th of a % of the time.
Right, exactly. Exactly, right. And also, the other way to think about it is, we are sitting on top of the cloud providers. And let's say you're sitting on top of EC2 in Amazon, and
Mm.
EC2 does not guarantee 4 nines, but we are guaranteeing 4 nines with Apache Kafka. So what you need to do is, Kafka has to be resilient to failures of your underlying infrastructure, which is
Yeah.
running at a lower availability than what you are guaranteeing. So that's why it's so important to fail over, to have all these replicas, to automatically detect these cases where something's going wrong with this underlying thing, which is flakier than than what you want to achieve,
Yeah.
so that you can give much better.
Yeah, because normally your availability goes down the more components you add. That's the default
Exactly.
reality. And to get past that threshold, that takes a lot of
Right.
work.
Yeah, I didn't even talk. Yeah, and then we have so many different components, and each of them has some availability. I don't think anyone gives us 4 nines, right? And then you're actually the sum of all the parts. So it actually gets worse if any
Yeah.
component failure will take you out. So that's why we have to be super resilient, that any of those guys can fail, and we don't fail, and we continue. And that's the only way to get to those 4 nines of availability.
Well, Adithya, keep fighting the good fight against the numbers.
Yeah,
Thanks very much for joining us.
Thank you. It was great talking to you.
Cheers.
Cheers. Bye.
And there we leave it. Now, if Adithya has left you hankering for more technical details on leadership election, then we do actually have an in-depth course on Confluent Developer that goes right into it and has some diagrams and walkthroughs and that kind of thing. We'll put a direct link to it in the show notes, or you can just go to developer.confluent.io and look for the course about Kafka internals with June Rao. It's part of our ever-increasing library of courses about Kafka and event systems, so it's a great place to go generally if you want to learn more. Meanwhile, if the quest to find and fix those curious performance edge cases at huge cloud scale sounds interesting, now's probably a good time to remind you that we're always hiring at Confluent. And I found it a great place to work, so come and join us. Take a look at careers.confluent.io for more. And with that, it remains for me to thank Adithya Chandra for joining us and you for listening. I've been your host, Chris Jenkins, and I will catch you next time.